So today we begin with the simplest logical system known as propositional logic. Some people also call it sentential logic. And any logical system consists of different components. And today we will look at the syntax of propositional logic. The syntax is a set of rules to construct well-formed formulas. You can think of the syntax and these syntactic rules as rules of grammar. Just like in English, we have rules of grammar that determine when a sentence is grammatically correct or not. In a similar way, in propositional logic, we have rules of syntax that determine whether a formula is well-formed or syntactically correct or grammatically correct, if you wish. And together with the syntax, any logical system has also a semantics. A semantics is, again, a system of rules to assign truth value to the formulas in the language. And we will talk about the semantics of propositional logic in another video. So let's begin with the syntax of a propositional logic. And as I said before, the syntax is a system of rules to construct grammatically correct sentences, grammatically correct formulas. The starting point are some basic ingredients of the language. Now, the first component of our language are so-called atomic statements or atomic propositions. These are typically denoted in symbol with lowercase letters such as P, Q, R, S, T, so any lowercase letter. This lowercase letter stands for any sentence that you want them to stand for. The computer is on the table, the sun is shining, etc. These are the basic components of the propositional language. They cannot be further analyzed. In this sense, they are atomic statements. The other components of the language are the operators that allow us to build more complex sentences out of the atomic sentence. These operators are also called connectives because they connect different statements or different sentences with one another. These connectives or operators are not, and, or, if then or implies, and if and only if. These operators or connectives are typically symbolized in the following ways, and since propositional logic is a form of formalized language, we will start using these symbols quite often. So instead of using not, we will use this symbol. Instead of using and, we will use this other symbol. Instead of using or, we will use this symbol. Instead of using if, then, or implies, we will use this symbol, this directed arrow from left to right. And then instead of using if and only if, we will use this double arrow that goes in both directions. Okay, so these are the basic ingredients of the language: atomic statements, propositions, or formulas on the one hand, denoted by these lowercase letters, and then these connectives or operators that by connecting together various sentences allows us to create more complex formulas. Now let's see how we can create formulas. And the definition of formulas here is in two steps, essentially: a simple step, a basic step, and then a more complex step. So what you see here as number one is the simple step, the basic step. Any of those lowercase letters denoting atomic proposition, formulas, or sentences belong to the language, belong to the set of well-formed formulas. So P, Q, R, and any of the other lowercase letters that we want to use. One note, this symbol that looks like an E means belongs to. So this expression P, E, L, P means that the proposition P, the atomic proposition P, belongs to the language of propositional logic, LP. So in other words, the sentence, the atomic sentence or the atomic proposition P is a well-formed formula of the language of propositional logic. And the same for Q, the same for R, and the same for any other atomic sentence or proposition. So this is the first rule to build a grammatically correct sentence. And you can see that this is a very simple rule. It's almost trivial. It's just saying what we consider a atomic sentence is, or atomic proposition is, a grammatically a well-formed formula in our language of propositional logic. Step 2 in our definition of a well-formed formula is more complicated because this is the step where our connectives come into place. So let's suppose that phi is a well-formed formula in our language LP of propositional logic. And let's suppose that psi is also a well-formed formula in our language of propositional logic. Now, these letters, phi and psi, are Greek letters and they stand for any well-formed formulas. So they could, for example, stand for P and Q if you want. They're just variables that stand for any possible well-formed formula. So we're supposing that we have already two well-formed formulas, phi and psi. So these are Greek letters. And then if we apply the symbol for negation not to phi, we obtain again a well-formed formulas. And so this is what this expression is saying, that the negation of psi is again a well-formed formulas of our propositional language. Let's now look at this other expression. This says that if we use the symbol for conjunction and we combine psi and phi together, we again obtain a well-formed formulas of our language. Now let's look at this arrow here. This, if you remember, is the arrow for implication. So this says that if we connect phi and psi, our well-formed formulas, with the implication, phi implies psi is again a well-formed formulas. Let's look at this other symbol here. This is the symbol for or. And what this says is that if we connect phi and psi with the symbol for or, we again obtain a well-formed formulas. Phi or psi is a well-formed formulas. And finally, if you remember, this is the symbol for double implication that stands for if and only if. So if we connect phi and psi with this double implication, we again obtain a well-formed formulas of our propositional language, LP. So as you can see, this clause number 2 tells us how to build more complex formula out of simpler formulas using the connectives. The connective negation, the connective conjunction, the connective implication, the connective disjunction or, and the connective double implication if and only if. And finally, there is clause number 3, which says that nothing else is a well-formed formulas in the language. There is a final observation to make here, is that we use parentheses here in clause 2, these parentheses are an aid for reading and parsing the formulas, but we can also avoid them if it's perfectly clear what we mean. The construction of formulas in our propositional language can be visualized in the form of a tree. And here we have two examples. The formula not P or Q implies R. This is an example of a formula that you can build. Or the formula not P or Q implies R. That's another example of a formula that you can build. Now, these formulas are built beginning with the basic component, the basic ingredients of our language, namely the atomic propositional sentences, which, if you recall, are denoted by lowercase letters, P, Q, and R. So these are the basic propositions, atomic sentences in our first formula, and again, P, Q, and R, the basic propositional sentences in our second example. Now we can use this atomic formula or propositions to build more complex sentences. And how do we do that? Well, we can use our connective or the operator negation, or, and, implication, and double implication. So you see that here, by adjoining the negation to the basic formula P, we can obtain the more complex formula not P. And then, interestingly, by conjoining together not P, which is itself a more complex formula, with Q, we obtain the even more complex formula not P or Q. And finally, by combining not P or not Q and R through the connective implication, we finally obtain the formula that we had here, not P or Q implies R. And we can do the same with the formula on the right-hand side. So we can use the connectives or to combine P and Q and obtain the formula P or Q. Then we can use the connective not to obtain not P or Q out of P or Q. And then finally we can use the connective implication to obtain not P or Q implies R. So the procedure is always the same. We start with atomic or basic formulas, and then we build more complex formulas using the various connectives or operators that we have.